I'm standing next to Trix, the Tyrannosaurus rex. We've just published a paper in which we estimate Trix's preferred walking speed. We did this based on a reconstruction of the tail, and you just have to look at the tail to understand how important it is for its walking. It's more than half of its length. The walking of dinosaurs was unique because of its tail. There's no animal alive that uses the tail in the same way. But why the walking speed? Well, when an animal doesn't have to run, it turns out that it tends to prefer a speed at which the energy expenditure is minimal. So it chooses a speed at which it expends the least amount of energy. This speed is so efficient because the animal chooses a step frequency, basically its walking rhythm, at which the body parts start to resonate. And in this case, the tail starts to resonate. But what is tail resonance? So to understand this, we should take a look at the real fossil, because as you can see from Trix's skull, the surface preservation is fantastic. But this might be even clearer if you look at the tail vertebrae. So this vertical stem is part of the vertebra itself, and at the front end you can see a transitional area, and then it becomes a bit prickly. You can see that on this one as well at the back. That is the ligament attachment. Well, we all have ligaments. Ligaments are like rubber bands. When you stretch them, they store energy, and when you let them go, they release the energy. But they don't use up any energy. So on this vertebra, my favorite vertebra, you can see that one of the ligaments has actually been preserved, and they actually ran between each vertebra. And that means that the entire tail was suspended at no energy cost. So the entire tail, by our reconstruction, almost 1,000 kilos, was really just a mass supported by a rubber band. And with every step, it would slightly bounce up and down. But you can see that if I choose the wrong rhythm, it costs a lot of effort for very little result. Whereas if I choose the correct rhythm, I suddenly get a lot of movement for very little effort. That's resonance. So, if T-Rex chooses the correct step frequency, the tail movements will be maximal. This maximizes energy storage and therefore walking efficiency. Essentially, the chosen step frequency has to be equal to the natural frequency of the tail, and we estimated the natural frequency using a biomechanical model. So if you're interested in the walking speed, it's not enough to estimate the step frequency. You also want to know how far apart each foot is placed. In other words, you need to know the step length. We estimated the step length by scaling up a fossilized trackway from a slightly smaller tyrannosaurid up to Trix's size. Next, if you multiply step length by step frequency, you get a walking speed that's slightly faster than 4.5 kilometers an hour. Now, interestingly enough, this is a lot slower than if you only look at these long legs. So who's right? Unfortunately, even though I would love to, I can't measure a walking T-Rex. But what we can do is look at living animals, like bipeds, humans, ostriches, tend to walk between 4 and 5 kilometers an hour. So that's also not that fast, but they're quite a bit smaller than T-Rex. So instead, you can look at elephants and giraffes. They're quite heavy, they have longer legs, but really, you find the same walking speeds. So it looks like T-Rex wasn't a very fast walker. But to be sure of this, we want to investigate more species. But one thing is sure, there's a lot you can learn from just the tail.